Hi there everybody. This is a video about how to find the length of a curve. If we get a straight line, finding its length is super easy. All it requires is the Pythagorean theorem or the distance formula, which is based on the Pythagorean theorem anyway. But if it's a curve, it's a little bit trickier. But we can approximate the length of this curve, which I've called y equals f of x, by using a series of straight lines. Right? We just connect a bunch of straight lines together where the endpoints are on the curve, and the length of those straight lines approximates the length of a curve. Now if we do that, the length of this segment here that I've drawn, I'm calling this delta x and this delta y. Using the Pythagorean theorem, the length of this segment here is the square root of delta x squared plus delta y squared. That's the length of this segment from here to here. Not the curve, but the segment. And we're approximating the length of the curve with the segment. And I'll show you how we get a better approximation in a second. But okay, so that's the length of the segment. I'm going to do a little, not magic, but a little bit of algebra here. I'm going to multiply this by delta x over delta x. Now delta x over delta x is 1, so that doesn't do anything to it. I'm going to take this delta x that's on the bottom, and I'm going to put it down here, squared. I'm going to put it underneath the square root and then squared. Okay, so I'm going to take this one away. So the square root of delta x squared is just delta x, and it was on the bottom. So again, I haven't changed its value any. I'm just kind of changing the way it looks. Okay, now if I divide both of these terms by delta x squared, I get the square root. Now delta x squared over delta x squared is 1. And I get delta y over delta x squared. Both of them are squared. I just combined them under there. And then I've still got this delta x on the outside. And again, that gives us the length of this straight line segment. Now, if I make delta x, smaller and smaller and smaller and smaller, and I add up all those segments from x equals a to x equals b, then delta x becomes dx, and delta y over delta x becomes dy dx. And if I go from a to b, since those are the endpoints of the segment, what I get is a way to find the length of a curve. So here is our formula for the length of a curve. Now there's two different ways to write it. Integral from a to b, we're integrating dx on this first way, dy dx in here. These are bounds for x since we're integrating dx. Okay. Now sometimes you have to do it dy, and I'll show you an example of that in a second. In this case, the derivative is dx dy. We're integrating dy, and so our bounds are for y, in this case c and d. But either one of these gives you the length of that curve, as long as you have y equals f of x. Okay. Now, these problems are fairly easy, so let's skip to some special cases here. Special case number 1, we've got a vertical tangent. Okay, it's the graph of y equals x to the 1/3 power. We've got a vertical tangent right here at x equals 0. And we want to know the distance from here to here. But if we turn this graph this way, it's no longer got a vertical tangent. It's got a horizontal tangent, but no longer a vertical one. So one way to do this, so this is one where we would have to do it dy. So we would write x in terms of y. Right? If we solve this for x, it would be x equals y to the 3rd power. That means that dx dy would be 3y squared. And so our length is the integral Now we're going to do this dy because it's got that vertical tangent there. And dy dx isn't defined. Like, we can't do it dy dx because it's not defined at x equals 0. So we've got to do, now dx dy is, 3y squared is always defined at x equals 0. So we've got to do it dy. So we got square root 1 plus dx dy. Don't forget the squared. It is dx dy squared or dy dx squared here. And we've got 2 squareds because our function had a squared in it too. Now our bounds, since we're integrating dy, our bounds have to be for y. That means we're going from -2 to 2. Plug that into your calculator and you've got the length of the curve. Now there's another special case, and that's corners. Here we've got a piecewise function. We got this line y equals -x plus 1. We've got this parabola y equals x minus 1 squared. The derivative isn't defined at that point. Dy dx isn't defined at that point. So what we've got to do here is separate it into 2 different lengths. Right? We want to go from x equals 0 to x equals, this is not drawn to scale here, that's why I'm hesitating. It's to x equals 2, which is up here somewhere. But if we can find the distance from here to here, and the distance from here to here, we can just add them together. For vertical tangents, you always got to do it dy. When you've got a corner, you can split it up into 2 different integrals. So our length, I'm just going to call it L. It's going to be 2 integrals. Integral. Now this first one's going to be from 0 to 1. Square root 1 plus. Now this is a line, and remember it's dy dx squared. And the derivative of this is just -1. So -1 squared. So that integral will give you the length of this first part, this diagonal line part of it here. And we're going to add to that the length of this curve. Now this actually you could have gotten just using Pythagorean theorem. And if you recognize that and want to do it that way, that's fine. Just know that this is a case, since it has a corner, where you've got to split it up into 2 parts. Okay. Find the length of one part, find the length of the other part, and add them together. Now this one, we're going from 1 to 2. Square root 1 plus dy dx squared dx. Now, this time our dy dx is the derivative of this. The derivative of that is 2 times x minus 1 to the first power. The derivative of the inside is just 1. So 2 times x minus 1. And there are our 2 integrals that, when added together, give us the length of this curve from x equals 0 along here to x equals 2.